Hey everybody, welcome to Tech Shorts, where every week we take you to the HPC engineering water cooler here in AWS and get you into conversations with some of the interesting technologists, engineers and architects who are making the cloud a better place for HPC. This week we're joined by Marco. Hey Marco.
Hi.
This is Marco Mastropolo, who was one of our software engineers in the DCV labs in Asti in northern Italy. Marco's in Turin today, working from home, like we all are, in extra special lockdown. So Marco works on our DCV team. DCV for us is a really interesting technology. DCV was created by a bunch of years ago to enable HPC users who had really big data sets that they were working on and wanting to visualize the data. We needed to be able to bring the desktop really close to the data without having to move vast amounts of data around. Now, in a normal HPC enterprise environment of the time, that might have been the data center might have been in a building across the campus or in a building a couple of buildings away, in a data center a couple of buildings away, rather than sort of being across the internet. As time has gone on, really large amounts of data have amassed in places like clouds where customers want to work on those things with HPC workloads. And this could be, simulating an oil field and doing seismic analysis of it. It could be doing fluid dynamic analysis of the hull of a yacht. And all of these things involve visualization of the final data. But of course, you want to be able to have a really close proximity between the GPU and the machine that's generating the pixels and the data itself, so that you can be much more sort of deliberate about the way that you slice and dice the data and look at it. So DCV was developed with this aim in mind of bringing those pixels much closer to the desktops and shortening that distance essentially, and frequently hiding the latency that came about from having a desktop a long way from that it was presenting. So thus was born DCV. Over time, we've seen DCV turn up in a bunch of different places. And so, Paolo, you've just been at GTC talking about how DCV turns up in gaming now. And that's a hugely different scenario than what we see in HPC. Talk us through this. What is this? What are we seeing?
This is New World. It's an upcoming video game from Amazon Games. And this is streamed at 60 FPS in Full HD from Dublin to Sicily, using SDCV, of course, using our QUIC protocol. And then the next video is a short demo showing the Great Drawing Room. Is a room in a museum in Stockholm. This is being shown with the custom engine that Giampaolo Ingegneri, one of our colleagues, did. This is great because it's being streamed again from Dublin to Sicily, but this one was in 4K resolution instead of Full HD. Again, right. At 60 FPS.
And again, I mean, we're using the internet here to actually stream. We're actually using the internet to stream pixels to a user's desktop, coming from a server that's actually rendering it on the fly, and and that could be really rich data set. It could be a game. It could be fluid dynamic simulation of the hull of a yacht. It could be any number of things. But of course, we're seeing it turn up in some weird places now. When we originally designed DCV, like most other things, it uses TCP as its transport layer for moving the packets over the internet between the data center and the desktop. And that's pretty common, right? But TCP was designed to deliver every packet faithfully, as you would expect for a network protocol moving data around. Everybody wants to have faith that their data is going to move around, but packets get lost on the internet. And given that we've all had the experience of using, of working from home. We're all of the victims of, what it's like to watch things that start to buffer. Everybody hates the stall that happens when buffering. And that's going to be really horrible when you're playing a video game, or, well, it's pretty terrible even when you're doing video conferences, right? So TCP is not exactly always the right transport, is it, for video?
Yeah, because TCP, well, it does a great job, but it's a protocol from the 70s, so it's great and it's evolved in the years, but it's trying to solve a general case problem, not a specific case. And the general case means that all data has to be received. While for video, it doesn't really make sense, and also for audio, usually, because, I mean, if we are doing real time, it's not really interesting if you are on a phone call, for example, to hear what you said 1 minute ago. It's probably expired, or you realize that it wasn't received, and you repeated the same thing. And the same applies to video. Receiving a video frame which is related to the past isn't really interesting, and losing time in retransmitting doesn't make sense.
And a video, a video frame that got lost from a quarter of a second ago isn't that interesting, but your eyeball will also smooth over the gap as well, won't it? Right? I mean, if there's 25 frames a second coming at you, and one of those frames get lost, it's not so bad, is it?
Yes, at the point where you lost a video frame from 1/4 of a second ago, the problem is that you see a jump, but you are seeing a jump anyway, even if we retransmit because the video stopped. So it just makes more sense to retransmit the current one instead of retransmitting the past. The past is gone.
So in an interesting way, this is similar to the problem that we often see in moving MPI packets around, which is it's a head-of-line blocking issue. So if all of the packets have to be delivered in order, and certainly in TCP they have to be delivered in order and at least read in order at the end, it really matters if one gets lost, because that causes all of the ones behind it to get backed up, which is what generates that buffering. Okay, so what we're seeing, and I know that we've got a graph here. Let me just get this up. So we've got talk us through this, and this is kind of the pictographic version of that discussion, isn't it?
Yes, this is, it's not real numbers, but shows what the different behaviors of TCP and UDP could be. I mean, in the best case, they probably perform the same or roughly the same. The problem happens when you have a packet loss, because for TCP, we have two behaviors which fight against us, let's say so. The first one is that there is a congestion window, which is shrunk because packet loss is interpreted as a sign that the network is congested, and so TCP just slows down and takes some time to recover. And the other one is the fact that TCP also, its general purpose, doesn't know that you are not interested anymore in past data, and so retransmits past data that we are not really interested on anymore. And so it takes a lot of time to recover from a packet loss on TCP and get back at the standard performance that we could achieve. On UDP, we still have to slow down if congestion is detected. Packet loss still has an impact because it's losing a video frame is not exactly free. We probably can talk about this later, but we can recover much faster because at the very least we can avoid retransmitting past data that we are not interested in, and we can also be faster and smarter at detecting if there is a congestion or not based on other factors rather than just packet loss, and so we can recover faster if the bandwidth is available.
Right. Okay, that makes sense. And so, but and I guess with TCP we don't get to make a choice, do we? If we're transmitting all the packets over TCP, we don't get to choose that we're going to ignore a lost frame. We don't want you to retransmit it, Mr. TCP. Just
correct.
On.
TCP takes control of that, so you don't have control on the packet has been lost unless you put a lot of amount of logic in a side connection or something like that, but it's really hard. You don't have control of the congestion window. You don't have control of a lot of things because the that's meant to solve the general case and be easy to use, let's say so. And does a great job in the general case, but for video streaming doesn't allow us to reach the top performance that we can.
Now, we've been talking about TCP versus UDP, right? And then, so that's what we got down here. But I mean, it's not actually, this is kind of like a metaphor in a way, because it's really not true. It's not really TCP versus UDP. It's really TCP versus UDP versus QUIC. Can you explain to everybody what QUIC is? Because a lot of folks watching are not web developers and they've probably never run into QUIC before. So how does QUIC differ from all of this, and where does it fit in?
QUIC is you can think of a middle in between of TCP and UDP. It's a transport like TCP and UDP, but it's sort of layered upon UDP because of historical reasons. Basically, all the appliances on the internet just expect TCP and UDP and ICMP. So it's not feasible to introduce a new one. You have to reuse one of those. And it offers, compared to just UDP, a lot of features, like, for example, it has encryption, which is out of the box. It has congestion control, which is out of the box. And it has streams, which behaves in practice in a very similar way to TCP connections, except that they don't have the head-of-line problem with their transmissions, because they can retransmit. They can transmit packets even if one of them was lost in the past, and just retransmit a single lost one instead of all the period from the lost one to the current, like at least original TCP without options does. And offers, on top of these, an optional extension, which is the datagram extension, which basically is UDP. It allows you to send raw datagrams and receives them on the other end, and having in this transmission a lot of control. Another thing which is good of QUIC is that it's implemented in user mode, and so it's possible for the applications to get a lot of control on what's happening on the network connection, and not just be passive, let's say so, about it, and stay at the TCP rules, but be proactive.
That's actually super important if you're actually wanting to implement something, say, in a web environment. I mean, that makes a lot of sense.
Yeah.
Okay, so we're actually using QUIC for our new transport in DCV, and that's some of the big work that you guys have done in the last several months is to build that stuff in. Where do we want to go now? Do we actually, is it worth actually discussing some of the video details here, because it's not really that we're just pushing individual frames out over the internet over QUIC between the server and the desktop. We're not literally just punching out frame after frame after frame, kind of like one of those old books you had when you were kids, where you flicked across 100 pages at a time and saw the little stick figure changing. It's not quite like that, is it? Because it's, we're using H.264, which has got iframes and p frames. Yeah. It's a little bit different, right?
Yeah, it's a little bit different because, as you said, we are using H.264, which means, let's introduce H.264. H.264 is a video encoder which has three kinds of frames. Frames can be transmitted in the three possible modes, let's say so. One is iframe, which is basically a snapshot of the boot screen, and they are good, like JPEG or something like that. They contain all the information for the current frame, and they are easily recovered. If an iframe is lost, we have to retransmit a new iframe with the same data, and that's it. But it contains also two other kind of frames, which are P frames and B frames. P frames are basically the differences from another frame in the past. So they P, I guess, stay for previous or past, or whatever.
really bad diagram here, it could actually be the guy's legs, the stick figure's legs that are moving. If the motion is happening in the bottom of the screen with the stick figure's legs, the p frames could just be his feet moving, right?
Correct.
And that would be those would essentially be the deltas between the original iframe going to the p frames.
Correct. And then we have B frames, which are also related to the future, but we usually don't use them because we don't have a future. We are in real time. The problem is that if you lose a frame in between, you also lose the possibility of using that frame in all P frames that are coming after that. And so if, for example, we lose the second one that you draw, and the third one was related to it for some reason, we cannot draw the third one because we lost the second one. And that is
and so,
yeah.
But I'm pretty sure that, so what's the big change that's in the most recent version of DCV, which is 2021.0, and we'll put a link up to that for everybody soon. And I'll make sure that the links are in the show notes at the end of this.
The big change in the newest one, which just released very shortly ago, like days ago, is that we can, if a frame is partially received, so we lost some parts or some parts are corrupted or something like that, we are able not to discard the entire frame, but to keep using parts of the frame that are received. So, for example, let's say that we are playing a driving game. Maybe there is a packet loss on the network. Maybe it's related to some part of the sky. We can still keep drawing the track and the car that you are driving and so on. And the part in the sky will stay still for 2, 3, 4, 5 frames, depending on how much time it takes to recover. But it doesn't need to get, I mean, we don't stop the video sequence just because one single part of the frame is lost. We just stop updating that single portion of the screen and we keep updating the rest at a constant frame rate. In the meantime, under the hood, we transmit back to the server the information that the part was lost, so that it can get retransmitted and we can recover the whole frame.
Okay, and that's important because it's packets that get lost on the internet, not frames. And so you're essentially saying, you know, like a frame might be composed of lots of packets that contribute to a frame. If you lose one packet here and there, it shouldn't be such a big deal. You know, we can recover from what we do know about the rest of the frame. And so we're working around that. That makes a lot of sense. That's going to be a huge efficiency, particularly in this environment where we're using things like H.264 compression to squeeze as much information in a short time as possible.
Yeah.
Okay. So what's the effect of all of this? I think you've got, talk us through this thing here, because you boost that up a little bit so everybody can see what the labels are. But you've done some experiments with all of this to see what different error rates and different packet drop rates might generate in terms of frames per second and throughput and stuff.
Yes, this is the frame rate measured on the client side using a domestic internet connection, so 100 megabit per second, like many homes have right now. Again, this was streamed from Dublin to Sicily, just as the video that we saw before. The first column is just the interconnection as it is. And so DCV 2021.0 over QUIC that we just released was able to keep a steady 60 FPS. DCV 2020.2, which is the version we released in the last December, so pretty new again over QUIC, was able to keep an average of 57, which is in practice very hard to distinguish from 60. It just means that sometimes it dropped below 60, but most of the time it was 60.
But
DCP over this was not able. Yeah, sorry.
Yeah, I mean, it's TCP is the staggering one here, right? It's a big
Yes, because the latency was too big, and TCP is also very sensitive to latency, and that means that it was not able to reach more than 22 FPS of average without increasing the buffering. But increasing the buffering means that also the latency of the input of a video game player or an artist drawing on the screen or things like that would increase because you are buffering video frames locally. And so that would be something that could be detrimental to increase that frame rate. It might be tuned to better values than 22 with manual tuning on your specific internet connection, but probably not much more than that without impacting latency too much. And
I mean, gamers are addicted to their 60 frames per second. You know, my partner's got a PlayStation in the living room, you know, a PS5, and you know, we had to spend a whole lot of money to upgrade the video in the living room so that we could get, you know, good 60 frames per second on a really big screen and so forth. Let's see what let's have a look at what this looks like in practice, right? Because we've got a video here and we can show everybody what this actually looks like. So let me hit the play button and please talk us through what's going on here so that everybody can see because this is the visual version of it all.
Yes, this is the demo of the Amazon Lumberyard engine. It's being streamed with NiceDCV 2021.0 over QUIC, and I don't know if it's visible from the video because of we are re-encoding right now in the streaming platform, but it was at 60 FPS when it was grabbed. And yeah, this is with the latest version with the partial frame recovery, as we said, and so on. This one now it's switched, and it is the previous version, which, as you can see, it's pretty much the same. It's very hard to notice the fact that with the standard connection, we dropped from the average of 60 to the average of 57. But yes, it's the same. Now it's switched to TCP.
TCP, yeah. And you can see the jumpiness, right?
Yes, you can see it's very jumpy right now. And yeah, TCP does.
But we've got, okay.
Yeah, this is side by side. Is the same as we saw before, just put side by side for comparison. And you can clearly see that the two versions with QUIC are pretty much the same or very similar. The difference will come up later. The one with TCP is not able to keep the pace, and it's really jumpy when playing.
And then we start introducing some drop packets, right? So that we're
yes. Now we introduce 1% of packet loss, which is a big amount of packet loss. It's a really lossy connection, and you can see that the QUIC ones are suffering a little because 1% of packet loss is not negligible. It's a lot of packet loss, and so they have to work a lot behind the scenes to keep a steady frame rate. But the one with TCP is basically a PowerPoint slideshow.
Yeah, it's suddenly just very stop motion. And
you can't play a game or interact with a computer at that frame rate.
My nephews trying to play games over the internet on their phones would not be very happy with this.
No. And this one is 3% of packet loss, which is if you have a rodent chewing on the cable or something like that, it's terrible packet loss. And at this point, you can see we don't show TCP at all because it doesn't make sense. But here you can see that sometimes the DCV 2021.0 on the left sometimes have small artifacts due to the fact that we try to recover partially lost frames. And on the other hand, the DCV 2020.2 doesn't have those artifacts, but is lower and isn't able to keep the same frame rate. We know that some people might prefer the old behavior in any case, and so there is a switch on DCV to choose which behavior if you prefer high responsiveness or high quality.
Wow. So So that's a really good visual. That's a really good visual of comparing data and techniques. So thank you for that. It's going to make a big difference if somebody's using DCV for doing remote desktop work at home because they're working from home during lockdowns. All of this technology that we've built in HPC is now spilling over into the gaming arena and all sorts of other streaming videos. So Marco, thank you for that. Now, your talk went live this week at GTC, right?
Yes.
And and you go into a lot more detail about this, right?
Yes, it's a lot more detailed with also details on what we changed on the GPU side and so on. And yeah, the NVIDIA GTC is free to attend. So if you are still in time to sign up, I encourage you to both see the video and the other videos at NVIDIA GTC.
It's actually incredibly important. That's really, really true. So we'll put a lot of URLs into the show notes at the end of the show. Here's how you can find more information on DCV straight away. You can find more info. You can look for the download page and start downloading DCV. DCV is actually free to use inside AWS. So if you've got an application running on an EC2 instance and you want to put a visualization aspect on it, you can bolt a DCV server on it. A few simple steps to do, and you can have the DCV server enabled, and it's license free inside AWS. And we have other mechanisms for purchasing licenses if you want to use it on-prem, because it's actually a pretty traditional way of running DCV as well, is on-premise. So, Marco, thanks for coming this week. I really appreciate the time. It was a really good discussion. And with that, we'll leave you. If there are any other topics that you want to hear us talk about on Tech Shorts, please send us a DM on Twitter. DMs are open. We're totally open to ideas about what we can cover in future shows. If you like what you see, please do click like and share with your friends and let them know the stuff that we're doing over here.